Hello. In our previous lecture, we have discussed about block ciphers. Block ciphers are a kind of symmetric key cipher, so encryption schemes. And we know that block ciphers, they operate uh, on blocks, not on bits. So now we are going to discuss about modes of operations for block ciphers. What is that? So when block ciphers are designed to encrypt data in applications, we can see that uh, it, it does encrypt a plain text block into a ciphertext block in a same way. So exactly when we have a same plain text block over and over, that means when we do the encryption, we can see the same ciphertext block over and over, because the way of encryption is the same. Number of rounds, the key generation, and everything is the same, and we can see a pattern of repetition uh, if you do the encryption. So, so because of that, an attacker who has some knowledge about the plain text, perhaps the knowledge about the plain text, can identify, okay, this plain text is going to be uh, this ciphertext, and then can identify the repetition paths. And from that, uh, the attacker is capable of finding the uh, value that is encrypted. So because of that, there's a necessity to do kind of a randomization of encryption. So that means when we encrypt the same plain text block over and over using the same key, it should compute a result of a ciphertext which is going to be different from the others. So even though the same plain text block is encrypted, ciphertext block is going to be different uh, in blocks. So that means randomized. There should be some way of randomizing the encryption. So because of that, these modes of operations are introduced to make the encryption randomized, even though we use the discussed kind of encryption schemes, symmetric encryption schemes, or block ciphers. So because of that, so there are like, so this slide will explain you the importance of that randomizing. So if if the encryption is deterministic, so try to understand these words. Deterministic means, so if we do something, output, we know the output. It is not going to be randomized. So without this mode of operations, encryption scheme, the AES or DES or whatever the encryption scheme we use, is going to be deterministic. So we have to make it randomized. The same plain text block is encrypted to the same ciphertext block every time. This allows the pattern to be found in long ciphertexts. To avoid that, we have to make the encryption scheme randomized instead of deterministic. So usually we prefer our encryption scheme to be randomized to prevent this, and typically this is achieved by using an initialization vector. So in this context, we use IV to indicate the initialization vector, which propagate through the entire ciphertext. The IV may need to be unique or random, and it is again a public value. Public means it is available to anyone. We cannot hide that. The only thing we are going to hide is the key, not the IV. But IV is used to do some kind of randomization, helps to do the randomization. So there are some important features on different modes which do not impact on security but are really useful for practical usage. So when we introduce different modes of operations, the purpose is to make the encryption scheme randomized, but as a result, there's no impact on the security. I mean, if you use one mode of operation to another one, so there's no impact on security. It is going to be secure. The same randomized encryption scheme, but the way it operates makes some differences. So we can use those differences. Because of those differences, we can use that encryption schemes for different, particularly for encryption, but also for other purposes as well. So some modes allow parallel processing because of that, the way they operate, and some will not help for parallel processing likewise. So some modes result in error propagation as well. A bit error in ciphertext result in multiple bit errors in the plain text after the encryption. Some modes require padding of data. Padding means kind of like a giving a pad. That means when we have a block, we have we have to add some bits in front at the rear end to make it for a certain length likewise. So that is called padding. Uh, some modes require padding of data up to an exact block length. Okay. So padding, the NIST means National Institute of Standard and Technology. This is US Institute for the Standards. So special publication suggests a padding methods as follows: append a single 1 bit to the data string, pad the resulting string by as few 0 bits as necessary to complete the final block. So likewise, when we have, let's say, 100 and let's say 104 bits plain text, and we consider a block of 10 bits, that means we have 10 bits and there is a 4 bits remaining. But for to use it for that particular encryption scheme, the block cipher, we have to make that remaining blocks, again we have to make another 10-bit block there. So for that we have to use padding. So padding standards are introduced. So padding bits can be removed unambiguously if the receiver knows the padding method. So that is fine. So there are different modes uh, like to make the encryption scheme randomized. So there are electronic codebook mode, ECB, cipher blockchaining, CBC, cipher feedback, CFC, output feedback, OFB, and counter mode, CTR. So I'm not going to explain you these modes, each and everything, but in this set of slides, you can see the clear picture about how these different modes are working. So you can easily understand it. When you are studying, just take a piece of paper and draw the diagrams and look at how the data flow is happening there. So the main thing you have to understand is in our block ciphers, the let's say like textbook block ciphers, we may use that term. Textbook block ciphers means the theoretical design of the block cipher, AES or DES. What we discussed in our last lecture, they are the textbook method of that block cipher. So in those things, we can see they are deterministic. Deterministic means when we do the encryption on the same block over and over, the result will be the same ciphertext block over and over. But that is vulnerable because attacker can get some information about the plain text. In long plain text, there's a possibility of repeating the same plain text block time to time, and because of that, attacker can gain additional knowledge, and using that knowledge, there's a possibility to decrypt the message. To overcome that, we have to make the encryption scheme randomized. To do the randomization, we introduce these kind of modes of operations. There are some additional thing, but then it will randomize the encryption scheme, and attacker cannot easily find the resulting outputs like that. And again, according to the way that modes or different modes of operations work, some special features will be coming into the different modes, and because of that we can use them perhaps in parallel, perhaps we can use them to another applications as well. So you have to understand that, and when you go through the set of the set of modes referring the slides, you can understand uh, the thing I explained. So these are the notations we use here. So the message block is N, and P represent the plain text message, C represent the ciphertext message, PT represent the plain text block T, where T is going to be uh, like between 1 and N. So some block, that means. CT represent the plain text block where T equals 1 to T is between 1 and N. So K represent the key. The key means here the master key. Using the master key, we derive round keys. We discussed that in our last lecture. And IV represent. IV is something in addition to what we discussed in our last lecture. IV represent the initialization vector. So you will understand how this initialization vector works in coming slides. So these are the modes. I'm not going to explain these modes. Instead of that, I can give you an assignment or some computation, so you can read the slides, understand, and do that assignment, because these slides are like very clearly explain how these different modes are working. So once you understand that, so these are some features of different modes. One is like self-synchronization. That feature comes into the picture when we use the CFB mode. CFB mode means cipher feedback mode. Cipher feedback mode, when you hear that, try to understand cipher feedback. The ciphertext is going to be the ciphertext block is going to be sent to the next encryption block as a feedback, something like that. And also there is a clear table saying the features, and you can easily compare the different modes after studying this set of slides. And after this, let's discuss about message authentication codes. So message authentication codes, they are used to introduce the integrity to messages. So message integrity is concerned with ensuring that message is not altered in transmission. So that means, let's say I send a message to my friend. When my friend gets the message, there should be a way for him to identify whether this message is altered during the transmission. So if I write a letter and give it to a courier service, and courier service guy will distribute it to my friend, there's a possibility that the courier service person can open the message and write something, change the words. But there should be a way that my friend should identify if there is if something is happening during the transfer. So to that purpose, that is called integrity. To that purpose, uh, there are several there are mainly two cryptographic mechanisms. One is digital signature schemes. So we will discuss about digital signature schemes in our in future lectures when we start discussion about public key cryptography. It goes into the public key cryptography category, but in current context, we are discussing about symmetric key cryptography or secret key cryptography. There, the mechanism we can identify for integrity is message authentication codes. This is very simple mechanism. So this includes preventing an adversary from reordering, replacing, replicating, or deleting ciphertext blocks in order to alter the deciphered message. Okay. So for this thing, the message authentication code is a cryptographic mechanism used for ensuring the message integrity. Integrity means there should be a way to identify whether the message is altered or not. That is called integrity, identifying that. And to that, in symmetric key cryptography, message authentication codes are introduced. So on input a secret key K and arbitrary length message M, a MAC algorithm outputs a short fixed length string. We call it a tag. So we use the letter T to indicate, identify tag. So T equals MAC. MAC means the message authentication code algorithm or function. And for that function, the input is, there are two parameters are used for the input. One is the M is the message, arbitrary length message, any length message that means, and K, the secret key K. They are the two parameters we give to the message authentication code algorithm or the function. So message authentication code will compute a tag using the plain arbitrary length message and the K value. So that is identified as the tag. So when so here we can identify that, we can understand it easily. A person A and person B are sharing a common key K. So there should be a way that the two people should share the key beforehand. That means by personally meeting each other, they can share a key, or using a different way of communication, they can, anyway, they agree on a key, K value. At this point, we are not discussing about how this K value is going to be distributed between two persons, but we know that K is prior distributed to the A and B persons. So they know that common secret key. The K value is only known to A and B. And A wants to send a message to B. So what A does is A computes the tag on the message M. T equals MAC inside brackets M comma K. And A sends message M in the clear and send the tag as well. So here, don't think that message is going to be like visible. So the idea of this integrity is not to provide the confidentiality, not to hide the message, but only to provide the integrity property, to make the other person aware whether the message is altered or not. So we are not considering about concerning about the confidentiality of the message. Message can be visible to the third parties or the public, but there should be a way that to identify whether the message is altered or not during the transmission. So that's the only concern in integrity. So compute the tag and send the tag with the message. So once the message, once the message is received, message and the tag is received to the person B, B will compute we will use the received message. We use the value m prime to indicate that is the message he received. He used that received message and he knows the k value, it is prior distributed. Using that, he compute the tag again, t prime. And then he can compare whether this t prime tag is it is matching with the tag he received, which is t. So if t prime and t is the same, that means m prime is same as the m. So the message he received is same as the message sent by the person A. So this is simply how the message authentication code, so MAC algorithms work, and this is how the integrity happens. And there are MAC properties. The above protocol provides sender authentication to the message, since only A and B can produce T from the message, because only A and B knows the K value or the key value. If T prime equals T, B concludes that the message received M prime was sent by A and has not been modified in transit. And if T prime not equals T, that means B must conclude that M prime is not the original value sent by A, because it results a different T value, because T prime is not equal to the T. The basic security property of MAC is called unforgeability. Forgeability means something like doing alterations, and it is not feasible to produce a message M and tag T such that T equals MAC M comma K without knowledge of the key K. So because of that that property, we can assure about the integrity of the message. So when you study about these different modes, you can see that CBC mode, cipher block chaining mode, that when we use cipher block chaining mode, you will see that there is a possibility to use that CBC mode block cipher can be used as a message authentication code. A block cipher can be used to create MAC, providing message integrity. So this is kind of a what we, as I told you earlier, this is a special property comes because of the mode of operation. So we can use this not only for the encryption purpose, but for message authentication code purpose, because of this additional property enforced because of the mode of operation. So you will understand this thing once you study about CBC mode. And so I didn't understand that, kind of like memorize. When you have different modes of operations for block ciphers, let's say AES or DES, then once we use the CBC mode, you can use that CBC AES or CBC DES for the purpose of message authentication codes or to provide integrity. Another thing is when we talk about the integrity or message authentication codes, there's another way of providing integrity, that is hashed MAC. So this is another method of constructing message authentication codes. One is CBC mode, and the other thing is computing a hash value using a keyed hash. So based on hash functions, we will discuss about hash functions in our future lectures, especially when we talk about signature schemes. We can talk about that. And HMAC or hashed MAC is basically a keyed hash function. So that means we just compute a hash value using a key and message M. So this is how this equation shows how that hash value is computed. First, the key XORed with some padding value, and that is concatenated with the message M and do the hashing, and that thing is again concatenated with key value XORed with some padding, and finally do the hash of that entire thing. So both hashMAC and CBC block ciphers can be used for message authentication codes. That means to produce or the provide message integrity in symmetric key cryptographic way. And combining encryption and message authentication codes. So when we combine the encryption and message authentication codes, Max, there are three possible ways to incorporate that. So one is first encrypt the message M and compute the tag or the MAC tag and send the two values. Encrypt will provide the confidentiality. MAC on M will provide the integrity. And the other way is first compute the MAC and get the T and then encrypt the message concatenated with the T or the tag and send the ciphertext. And the third way is encrypt the message to get the ciphertext, then compute the MAC on that ciphertext and send to the results. There are three possible ways, and from these three possible ways you can identify that once the message is encrypted we can get the ciphertext, and once the message is used to compute the tag, even though it provides both confidentiality and integrity, we can see that for the to create the tag, the MAC tag, we just use the M value, the plain message. So if there is a way or the vulnerability in message authentication code, using that from that T value, there is a possibility to get the idea about the M value, even though it is completely hidden by the ciphertext. So first mechanism obviously shows some weakness, and the second mechanism, MAC M to get the tag value T and then do the encryption. But here you can see that the plain message is again used to do compute the tag value and then encrypt that concatenation and send the ciphertext. So this is better than the first choice, but when you see the third one, that is first we do the encryption of message, then create the ciphertext, and using that ciphertext tag is created. So you can see that only that publicly visible value, the ciphertext value, is used to create the tag value. So because of that, it is more efficient and more secure. So it turns out that encrypt then MAC, or the third value, the third way is the safest approach. First create the ciphertext, and using that ciphertext create the MAC value and send the concatenation of ciphertext and tag. So that is going to be the safest and most efficient way. And this is some a little more information about authenticated encryption, as we discussed in our previous slide. That is to provide both integrity and confidentiality. So authentication means that there is some authentication, like who sends the message, some guarantee who sends the message. So that means that ensures the integrity. So SSL version 3.0, TLS version 1.0, TLS version 1.1, MAC then encrypt is enforced. This has resulted several security vulnerabilities, and because of that, TLS 1.2 supports uh, counter mode with CBC MAC uh, for the operation. So not just the MAC then encrypt. So this is enforced explicitly. CBC mode should be used, and there are several more efficient techniques for authentication encryption, but not widely adopted. One is OCB mode, and other one is CAESAR, authenticated encryption competition. It will give a result. Okay. So this is a little bit information about how we prevent that deterministic encryption and make it randomized, and as a result of that we can use different modes for different purposes, like parallel encryption. So like we can do the encryption parallelly to blocks, and some modes will not support parallel encryption because uh, you can see that the ciphertext of the previous block will be used for the use as the initialization vector of the next block likewise. So you will understand that once you read the slides, and then you have some idea about authenticated encryption. To provide both encryption, the confidentiality and integrity, you can use MAC and encryption. Okay, so this is some more information about what we call the the block ciphers. Some additional means some like the real world usage of block ciphers, and from next lecture we will discuss about public key encryption schemes. So the major difference between symmetric key and public keys: in symmetric key, both sender and receiver use the same key, same master key, for the encryption as well as decryption. But in public key encryption, one key is used for the encryption and another key is used for the decryption. So these two keys should have a mathematical relationship between them in a way that it will give the correct encryption and decryption. Okay.